this video, we'll discuss the concept of classification matrix. Classification matrix is a very important concept employed to examine the efficiency of a classification algorithm such as logistic regression. Recap: in the previous video, we introduced the concepts of or the errors known as false negatives and false positives. Let us elaborate in more detail now. We noted that there are cases, and we'll carry with our example of default and non-default. Remember, we classified y equal to 0 as cases of non-default. Now, cases where your regression algorithm like a logit regression or classification algorithm like logit regression, those cases that are actually non-defaulters and correctly predicted as non-defaulters are considered as true negatives. Similarly, those cases which are actually non-defaulters, that means zeros, but incorrectly classified as defaulters or ones, they are considered as false positive. Similarly, those cases that are actually defaulters or ones but incorrectly classified as non-defaulters or zero, they will be called false negatives. And conversely, those that are actually ones but predicted and also predicted as ones, that means defaulters, correctly predicted as defaulters, are considered as true positives. Now, this matrix is often referred to as classification matrix or confusion matrix, and various efficiency measures, various efficiency or accuracy measures to understand the accuracy of a classification algorithm like logit model is derived from this matrix. Let us look at two very important parameters that are derived out of this matrix. First is sensitivity. Sensitivity is nothing but the ability of our model to correctly classify true positives out of total positive cases. So for example, total positive cases are true positives plus false negatives. So actual ones are true positive, false negatives plus true positives, which are here in denominator, and in numerator we have true positives. So this is called true positivity rate. Similarly, we have another measure defined as specificity. Specificity is nothing but overall true negativity rate, which is true negatives on the numerator divided by true negative plus false positive. Now, as you would have understood now by our discussion of thresholding, there is a trade-off between sensitivity and specificity depending upon our value of threshold. Recall that diagram of tau thresholding discussion where we said that, let's say, these zeros are our defaulters, these zeros are our defaulters, and these crosses are non-default cases. And remember, we said that a high value of t, if you pick a very high value of t, let's say 0.8, like this, there's a possibility, a high possibility, that some of the default cases or y equal to 1s will be incorrectly classified as y equal to 0s. That means a high false negative rate, false negative. This means because your false negatives are larger, your sensitivity will be low. What about specificity? Since you have taken a very high value of t or tau, the possibility that you will incorrectly classify non-defaulters as defaulters is very low. That means your false positives are very low and you score high on specificity. So you score high on specificity but low on sensitivity if you choose a high t. Vice versa discussion applies for a lower t. That means if you pick a very low t, low value of tau or t thresholding, we are interchangeably referring to this t or tau, then in that case, remember, most of the defaulter, in fact all of the defaulter chances are you will classify correctly as defaulters. So your false negative will be very less and your sensitivity will be high. However, at the same time, if we talk about specificity, there is a chance that some of the non-defaulter cases may be classified as defaulters. That means a high false positive number, and therefore your specificity will be low. So if your tau or thresholding t value is low, then you may score high on sensitivity but low on specificity. So depending upon your selection of tau, your sensitivity and specificity measures will vary. There are some other important measures of efficiency or accuracy of model prediction that are also computed. You do not look at one measure, but you look at number of measures. For example, there is a measure of overall accuracy, which sees how many true negatives and true positives. That means how many zeros you collect. True negatives are the zeros that you actually classified as zeros, and true positives are the ones that you correctly classified as one. Divide by total number of observations. So this is your overall accuracy. Similarly, overall error rate. So false positives, those are zeros that are incorrectly classified as ones, and false negatives, those are ones that are actually classified as zeros. So both are inaccurate classifications divided by total number of observations. So this is our overall error rate. Another measure is false negative rate. That means overall, what is the incorrect classification for the actual y equal to ones, in this case defaulters, that is incorrectly classified ones. So that those that are ones incorrectly classified as zeros divided by total number of ones. How do we arrive at total number of ones? That is true positives ones that are classified as ones, and false negatives ones that are incorrectly classified as zero. So the denominator is total number of ones and numerator is only those ones that are classified as zero. Similarly, we have false positive rate. False positive rate is theoretically those that are zeros incorrectly classified as ones. So numerator we have zeros incorrectly classified as ones, and they are divided by in denominator by total number of zeros. That means true negatives, zeros that are classified as zeros, plus false positives, that means zeros that are classified as ones. So this is false positive error rate. To summarize this video, we discussed a very important measure of model accuracy, which is confusion or classification matrix. Based on confusion and classification matrix, we derived two important measures of sensitivity and specificity. We noted that selection of thresholding value, a very important concept we discussed in the previous video, is a trade-off between these sensitivity and specificity. Next, we also derived a number of very important measures of overall accuracy of the model prediction, overall error rate, false negative rate, and false positive rate. Essentially, all these measures are derived out of confusion and or what we call classification matrix, as we discussed in this video in detail. In this video, we'll discuss receiver operator characteristic curve, which is a very important visual measure of the accuracy of classification algorithm. Recall our discussion on true positives and false positives. Remember, true positives are same as sensitivity measure, and false positives are 1 minus specificity measure. We discussed these formulas in the previous video. Now let us plot true positive and false positive rates on the y and x axis respectively. True positives are essentially the proportion of default cases, that means ones correctly classified as ones or sensitivity. False positives are non-default cases, incorrect, or that means zeros in our case, incorrectly predicted as default cases or ones, which is 1 minus specificity also. So on x-axis we have false positives and y-axis we have true positives. So x also sensitivity on y-axis or 1 minus specificity on x-axis. Now a curve like this indicates the model performance, how these rates of sensitivity and 1 minus specificity vary depending upon different threshold values. Let us discuss this in more detail, but this behavior, this movement is essentially what we call as ROC or receiver operator characteristic curve. Let us start with the case of thresholding value of tau or t equal to 1. In that case, our true positives will be 0. T equal to 1 is an extreme case where all the cases will be considered as non-defaulter. So all the loan applications, or what we call as whether they are zeros or ones, they will be considered as zeros. That means none of the cases will be classified as ones. Even the ones, all the ones will be classified as zeros. And therefore true positive rate is 0. So on the true positive rate or sensitivity of the model is here 0. But at the same times, because we are not classifying any case as 1, even those that are zeros, all the zeros are collectively classified as 0. So none of the zeros are also classified as 1. So this is one can say a sort of positive from this model, that none of the zeros will be classified as ones and therefore false positives will be 0. So this point will be here as well. So for t equal to 1, irrespective of the logistic regression or a classification algorithm model, its coordinate will be 0, 0 for t equal to 1. This is irrespective of the model, it will always be 0, 0 here. Now think of another extreme case where t equal to 0. In this case, if t equal to 0, all the, whether it is zeros, defaulters, or zeros or non-defaulters, or 1 or defaulters, all of them will be classified as defaulters, that is ones. That means all the defaulter cases ones are of course classified as ones. So our true positivity rate is 1, our sensitivity is 1, true positivity and sensitivity are same, so we are standing here. But the same times our zeros are also getting classified as ones. That means false positive rate is also 1. All the zeros are classified as 1, so our specificity or false positive is also 1, so we have this coordinates. Again, this is irrespective of the model. Whatever model you choose, the for t equal to 0, this point will always be 1, 1. However, for all the other cases, different models will show different behavior. Except these 2 points, all the models will show different points, different behavior. So as we move from t equal to 1 to 0, we will move on some curve like this. And one can judge the accuracy of model as per area under this curve. For example, whatever area under this curve as a percentage of overall area will reflect the accuracy of this model. Let us discuss this in more detail. Here, this ROC curve, the behavior of this ROC curve captures the complete threshold behavior of our classification algorithm. For example, at different threshold values, this model will have high or low specificity and sensitivity. For example, if you have high threshold value like t equal to 1, this model will have very high specificity, that means low 1 minus specificity, it will here, somewhere here, and low on sensitivity. At the same time, if you have very low threshold value, the point is somewhere here, that means low on specificity but high on sensitivity. So there's a trade-off between the cost in failing to detect cases versus incorrectly considering non-default cases as defaulters. So there's always a, depending upon the threshold value, there is a trade-off. And this trade-off is very nicely captured by this ROC curve. For example, if I move from initially, if I increase the threshold value in this region, notice how sharply, because the curve is very steep in its slope, how sharply my true positive rate or sensitivity of the model increases. That means my ability to classify correctly ones into ones increases very sharply. At the same time, the fall in specificity here, because we are plotting 1 minus specificity, so rather the fall from 1 to these lower values is very small. So notice in this region my sensitivity gain is very high as I increase my thresholding value, but my loss of specificity is very less. At the same time, as I move in this region, please notice my gain in sensitivity is very small because now the curve has become flatter, but my loss is in specificity very, very high. So I would rather be somewhere here. This may be one of the optimum points, but again it is subjective, depends on individual objectives of the entity which is doing the modeling, but still it seems to be a good place to be here because here we have lot of gain in sensitivity and the loss in specificity is very small. Finally, an ideal but a more of a theoretical case would be 100% score. That means all the observations are correctly classified, and in that case your movement, that kind of model, if that were to exist, although it will not, but if there is a model that completely and accurately classifies with 100% accuracy all the observations, it will move like this. And therefore the area under the curve for this kind of curvature which is moving like this is 100%. It captures everything. That means all the observations are correctly classified, so true positivity rate is 1 all the time and false positivity rate is 0 for all the thresholding values. But this is more of a theoretical discussion. Let's take a random model where there's a 50% probability, which indicates almost like a random guessing, a coin tossing, a fair coin toss, where 50% probability you can get a head or 50% probability you can get a tail. In this kind of model, you have for all the times your true positives is 0.5 and false positive is also 0.5. So on this behavior, which is like a 50-50 model, your movement will be reflected by this kind of curve. So it's always 50-50, and therefore area under the curve will be 50% of the overall area. This is like a coin tossing game, and this model is no good than a coin toss, random guessing. For more practical models, they will lie somewhere in between. That is from 50% to 100%, they will be somewhere in between. And therefore, the accuracy of the model can be very nicely measured as the percentage of area under this curve, this ROC curve. To summarize this video, we discussed the ROC, receiver operator characteristic curve. In this curve essentially provides a visual examination of the efficiency of the classification algorithm. Here on the y-axis we have true positive or sensitivity rate. On the x-axis we have 1 minus specificity rate, or what we call false positives. We noted that there are two extremes to this model. One, those models, purely theoretical models, which classify every observation correctly, and therefore the area under the curve of such model is 100%, while then there are cases where 50-50 accuracy is there. For them, like this kind of 45-degree straight line, area under the curve would be 50%. This ROC curve essentially captures the behavior of any classification algorithm depending upon different threshold values. So it captures the thresholding behavior at different thresholding levels for a given classification algorithm, and the accuracy of any classification algorithm can be measured as area under its curve. And we noted this area in normal practical cases should lie between 50% to 100%, where these two, 50% and 100%, are two extreme cases, and lie somewhere in between. We also noted that for all the models, 2 points, two extreme points, that is thresholding value of t equal to 1 and t equal to 0, are the same. In this video, we'll talk about parameter interpretation of logit class of models. Recall our discussion about simple linear regression model of this form, where we said yi equal to alpha naught plus alpha 1 into xi plus the error term mu I. We said that here the interpretation of parameter alpha 1 goes like this. If xi and yi are absolute form, then 1 unit change in xi will result in alpha 1 unit change in yi. If xi and y are in log form, then percentage change in xi, 1% change in xi will reflect in alpha I percentage change in yi. And if we were to plot this, it would appear like this. X, y on xy axis, this would appear like a straight line where alpha naught and the slope of this line will reflect alpha 1. So this is our OLS fitted line. However, the interpretation is not as simple in the logit class of models, because essentially these are non-linear in parameters. Why this is important is because remember our logit function, which is essentially the probability that yi equal to 1, is reflected as 1 plus 1 upon e to the power minus zi, where zi was a linear function of xi's. This is a vector of various x's. So it will be something like beta naught plus beta 1, x1 plus beta 2, x2, and so on up till beta n xn plus the error term. So recall, this is the form of function which was non-linear in nature, and its behavior on xy axis is captured like this, like a S curve, where the limiting cases are 1 and 0. So on the left side the limiting case is 0, and on the right side the limiting case is 1. Now such behavior, which is non-linear in nature, it requires high school mathematics to understand that the impact of this zi on yi varies. Here this x essentially, it captures the dynamics of zi, which is this function. So here the impact of zi on yi varies depending upon where you are on this zi. For example, if you are here, if you want to compute the impact here, recall our high school mathematics that the slope of yi, that means the slope of this function dp, let's call this function as pi, dpi upon dzi, this slope, which is reflected by the slope here on this curve, measures the impact on yi at this particular point. Similarly, If you want to measure impact on at any specific point, you need to compute the slope. So let's say you want to compute the impact of a particular variable x2i on zi. The most appropriate way to find that impact is the differential with respect to that particular variable, and this is what we call as marginal effect. So to put things in perspective, in this kind of model, it is not correct to say that 1 unit increase in x2i will cause beta 2 percentage increase in the probability of yi, which we said in the LPM model. Remember, in linear probability models, LPM models, we simply said that beta 2, the coefficient of that model, yi equal to beta naught plus beta 1 x. In case of linear probability modeling, we said that this beta 1 is nothing but 1 unit increase in xi will result in beta 1 into 100 percentage increase. Rather, I should write it as beta 2 and this as beta 1. So 100 into beta 2 times percentage increase in probability of yi equal to 1. This kind of statement we cannot make in the logit class of models, and like we discussed in the just a few seconds ago in the previous slide, this has to be calculated in this form: dpi upon d of x to y, which is nothing but the slope. Remember, we computed at any point, we computed the slope. This slope represents for a variable x2, this would represent dpi upon x2 dx2, where on y-axis we have pi, on x-axis we have x2 I variable. Now, for logit class of models, if one computes using that function 1 plus e to the power minus zi, where zi was the linear function of variables x1i, x2i, and so on, this works out to beta 2 times f of x2i, where this is f of x2i and 1 minus f of x2i for the logit model. So a 1 unit increase in x2i will result in the probability of yi equal to 1 by beta 2 times f of x2 into 1 minus f x2i, where f of xi is the logit, cumulative logit distribution function, which we have discussed in previous series of videos in the lesson. And these are called marginal or incremental impacts evaluated. And these are often evaluated at mean values of these variables like x1i and x2i, as we'll see through a simple numerical example. So have a look at this function of a probability function, logit class of function, where the value of zi is reflected with this expression. This is essentially 1 plus e to the power minus zi, where zi is captured by this expression. Now here, the variable, the parameters of beta 1, beta 2, and so on are already estimated here. We can see them: beta 1 is 0.1, beta 2 is 0.3, and so on. Now here, if you are asked what is the value of fzi, it is very easy to calculate. We'll calculate them at the mean values of variable. Let's say the mean values of x2 bar, x3 bar, x4 bar. It is customary to compute the marginal effects at mean variable, although you can compute at any given values. So at these mean values, we'll compute the value of fzi first. And if you are asked to compute the marginal effect, let's say marginal effect of x2i, then you'll compute using this formula: beta 2 into f of x2i into 1 minus f of x2i. So first we'll compute the value of fzi at the mean values. It works out to mean values, that is x2i bar, x3i bar, and x4i bar. At the mean values, we'll fill the mean values as we saw in the previous slide. These mean values are available to us. Using these mean values, we'll compute the value of fzi, which works out to 0.63. Now that we have mean values, we can simply compute this expression: beta 2 times f of x2i into 1 minus f of x2i, which works out to beta 2, which is 0.3, into f of x2i. This essentially works out to same as f of zi, which is 0.63 into 1 minus 0.63. So this number. Similarly, for x3i, we will multiply it with beta 3. Other values will remain same: 0.63 into 1 minus 0.63. For x4i, it will be 0.9 into 0.63 into 1 minus 0.63. These are what we are calling as dpi upon dx2i or dpi upon dx3i. These are often referred to as marginal effects or incremental effects, or the impact of coefficients. 1 unit change in the coefficient, the impact on percentage change in probability. This can also be interpreted like that. To summarize in this video, we noted that unlike linear probability models or simple linear regression models, the impact of individual variables like x2i, x3i, and so on cannot be simply measured in the form of their respective betas like beta 2, beta 3, and so on. In the case of these logit class of models, one needs to calculate the differential impact, or what we call marginal effects or incremental effect, in the form of this expression dpi upon dxi. And the value for logit class of model works out to simply for a coefficient xi as beta I into 1 minus f of xi into f of xi. And these marginal effects are nothing but simply the slope. Remember the behavior of this S curve, the logit model S curve. This is nothing but the slope of the curve at any given xi. At any given xi, the slope where y-axis is pi, the slope is the marginal effect, which is computed with this formula in the specific case of logit function. In this video, we'll briefly summarize three important topics, which is probit model, maximum likelihood estimation MLE, and goodness of fit measures. The mathematics can be ugly and out of the scope of discussion. Only a brief summary is warranted here. First, let us quickly summarize the probit model. The probit modeling approach is very similar to logit model. In fact, it is almost identical, with the only difference that the function, the distribution function, is changed to normal distribution. So now our fzi, which was the cumulative logistic distribution function earlier, it is now cumulative normal distribution function. Remember, the normal distribution function appeared somewhere like this. Starting, it appeared like this, and its cumulative, this is the normal probability density function. Its cumulative function would appear something like S curve, slightly different than the logit curve, but still like S curve, starting from 0, lower cutoff is 0 and upper cutoff is 1, because it is a probability density function. So the cumulative function would of course start from 0 and cut off at 1. In functional form, this appears like this: fzi is equal to this complex looking function. However, we need not remember that formula. There are computer programs, and as we'll work on our, it will be automatically clear. Now, the properties are exactly same as logit function. As z tends, remember that if z tends to minus infinity, this function approaches to 0, and if z tends to plus infinity, it approaches 1. So that is a very desirable property for this kind of modeling. Second, the marginal impact, the interpretation of marginal impact of xi on the probability function remains identical. Only when we derive this formula of marginal impact, that is dpi upon xi, the resulting formula is this one, which is slightly different. It is beta 2 times fzi, where beta 2 is the parameter attached to x2i. And remember, what was here zi? Zi was beta 1 plus beta 2 plus x into x2i plus beta 3 into x3, and so on. Next, we'll summarize the maximum likelihood estimation of logit probit models. Recall that these are non-linear models in parameters and hence cannot be estimated with a simple OLS method. They are estimated with the help of MLE. And in MLE, parameters are chosen to maximize the log likelihood function, as we'll see. And this log likelihood function obtains the population parameter estimates that maximize the joint probability of observed sample or sample parameter estimates. Let's discuss this in more detail, what exactly this is. And recall our discussion that essentially what we have is a set of population parameters. That means we have a set of population regression function which maps the observed yi from a given set of variable x2, x3, x4. These are our variables which map through population regression function, where parameters may be beta 1, beta 2, beta 3, and so on. However, we do not have the luxury of working with population, but we work population, which is a very large sample of data which maps from xi to yi. We work with a rather small sample, and we estimate what is called sample regression function, SRF, which tries to map these variables x1, x2, x3, and so on with our variable of interest yi as dependent variable. But here what we estimate is beta 1 hat, beta 2 hat, and beta 3 hat, and so on. Now please remember, for each observation, for each yi, let's call it each yi observation which is part of our sample, a set of parameter estimates may be there. So each observation yi can be associated with the parameter estimates. For all times, we remember we do not have the population parameter estimates, we have sample estimates. And for each observation, a set of estimates may be used. there. So for example, y1i, y2i, these are different observations of the yi which map from these xi observations, x1i, x2i, and so on, where a certain set of parameter estimates may be more likely, and so on. Now, for each observation yi, we have a set of parameters. Let's call them the entire parameter. Let's call them beta vector, which is a vector of parameters. Beta, let's call it beta k vector. And for each observation y2, we have a different vector. Let's call it beta1 for y2, b2, beta2 vector, and y3. Let's put it in capital B. So b1, b2, these are vector of parameters for each observation. Now, what we are doing here, we are trying to find the probability. We are trying to find the probability of observing this vector of parameter estimates, and let's call it p1, p2, p3. For a given set of original parameter, which is b, there is a certain probability of observing this parameter estimate p1, p2 for this set of vector, p3 for this set of vector, and then ultimately, if you want to jointly maximize this probability of observing all this, that is p1, what will be the joint probability of observing all these parameter estimates, p1 into p2 into p3 and so on up till pn. If you have an observations, then this is the joint probability of having these observations, and each observation maps to a particular set of parameter estimates. Then essentially, as a part of MLE, what we are doing, we are trying to find those population parameters, those population parameter vector v which maximizes this joint probability of observing the sample parameters. I repeat, just to summarize, essentially as a part of MLE, we are trying to find those population parameters that maximize the joint probability of observing these sample observations, where each observation corresponds to a set of likely parameter estimate, probably p1 with beta 1, p2 with beta 2, and so on. And this population parameter, which we estimate from MLE method, maximizes the joint probability of observing this sample data. In the last part of this video, we'll summarize the goodness of fit measure that are more useful for logit probit class of model. Remember, the conventional R-square and adjusted R-square measures do not work well with the logit and probit class of models for the simple reason that unlike OLS, ordinary least square regression model, ordinary least squares, where we minimize the residual sum of squares, RSS, of the error terms, residuals, unlike that, MLE aims to maximize the log likelihood function that we just discussed, which is the joint probability maximization. And therefore, the conventional R-square and adjusted R-square measures do not work well. So there are two very simple and very intuitive measures that are employed by logit probit functions. One is the percentage of values that are correctly predicted. This is often referred to as naive model problem, where you try to find what percentage of yi values you are correctly predicting. So there are total number of values that are correctly predicted, divide by aggregate total number of observations. The other way would be percentage of y equal to 1, that means positive cases that are correctly predicted, and percentage of y equal to 0 cases that are correctly predicted, and that is your accuracy of the model. You can take some sort of average of percentage of y equal to 1 correctly predicted and percentage of y equal to 0 correctly predicted to reflect the accuracy of model. Obviously, you can change the weights also. For example, if you feel that y equal to 1 correctly prediction is more value, then you give a higher weight rather than 0.5. You can give it a 0.7 and so on, and then 0.3 to this. Similarly, if you feel this i equal to 0 is more desirable, then you give a higher weight to this one, maybe 0.7 or 0.8, and the remaining 1 minus w to this one. So if you assign 0.8 here, then 0.2 here, and so on, so that w1 plus w2, the weights are 1. Also, there's a very interesting measure which is pseudo R square, which is employed. Pseudo R square formula is very simple, 1 minus LLF upon LF naught, where LF is the maximized value of log likelihood function that we discussed. Remember, P1 into P2 into P3 and so on up till Pn. This is the joint probability that we maximize with respect to parameter beta I. We try to maximize this function. So this is the joint probability maximization for logit and probit class of models. And LLF naught is considered to be the restricted model, where it is assumed that all parameters are relevant. That means beta 2, beta, and jointly all these parameters are 0. So the restricted function assumes or calculates this joint probability for a model where all the parameters are assumed to be 0. So that is your restricted model, and then you compute for the maximized value for those parameters, beta 1, beta 2, and so on, where this function, this joint probability function of observing the parameter estimates is maximized. So LLF is the maximized value of log likelihood function, and LLF naught is the likelihood function for a restricted model where all the parameters are assumed to be 0. Now, this expression has a very interesting property, and that goes like this. If your model is very poor, if your model is very useless, that means all the beta 1 and beta 2 and beta 3s are not contributing to the explanatory power. In that case, your LLF value will almost be as close as LLF naught. That means your maximized value with will be same as LLF naught, because your parameters are not so useful. So that means even whether you have these parameters in the model or do not, the explanatory power of your model is not so good, and therefore your LLF maximized as well as LLF naught for restricted model will be close to each other, and therefore this value will turn out to be 0. So this is one limit. Other extreme case here is that your model is very well specified, and therefore this LLF value is extremely large as compared to LLF naught. In that case, please remember that this log likelihood, essentially this LLF is log likelihood function. That means it is a log of some probability number where probability is moved from 0 to 1. If your model is very well specified, let's say it is a very good model where probability is almost inching towards 1, which is an ideal case where it is almost inching towards 1, then this log of this value LLF will be closer to 0, because the likelihood functions are probabilities, and when probability is approaching 1, the log of likelihood, this is log likelihood function, this will approach to 0. However, because your LLF naught is very poor, this value will be very close to 0, assuming that relatively it is very poor, it will be much closer to 0, and therefore essentially if you look at this number, the log of this number will approach minus infinity. If this value as LLF naught approaches 0, this value will approach minus infinity, and therefore the ratio will approach 0. While these were limiting cases, but you can imagine this LLF naught, as long as this ratio, this number inches, the probability inside log of a number probability, which is relatively much higher as compared to the denominator, this number will approach 0. The idea is that in the case where the model fits well, the log of probability will approach a reasonably large number, while the denominator approaches to very large number, and the magnitude of this number inches to 0. And therefore, the upper limiting case of this function becomes 1. So this pseudo R square, very similar manner to conventional R square or adjusted R square, will range from 0 to 1. So this is how we use goodness of fit measures for the logit probit class of model, which are slightly different from the conventional class of goodness of fit measures such as R square and adjusted R square. To summarize this lesson, among supervised learning models, classification algorithm is a very important tool employed in the finance domain for applications such as credit scoring of loan applications. Classification algorithms are often implemented through logit probit class of models. These are very simple yet powerful models. These models account for a number of shortcomings of linear probability models, such as first, non-normality and heteroscedasticity of error terms. Second, the values of dependent variable or the probabilities cannot exceed the 0-1 range. And third, the diminishing utility of conventional measures of goodness of fit, such as R square measure. The limited dependent variable models, such as logit model, employ cumulative probability functions, such as logistic function. These models, although nonlinear, are very useful for modeling limited dependent variables that are probabilistic in nature. In the case of the logit model, the logit function is essentially the odds ratio. Since the estimated variable is in the form of probabilities, the thresholding process is required to convert these probabilities into limited outcomes such as yes, no, or 0, 1. The conventional measures of goodness of fit such as R-square are not very useful for such models. These measures are evaluated on their ability to accurately classify observations correctly. The receiver operator characteristic curve provides another useful tool to examine the efficiency of these models and also facilitates the selection of thresholding values. Unlike simple linear models, the parameter estimates are interpreted in different manner as we discussed in the form of marginal impact. These marginal impact or marginal effects are computed to interpret the coefficients and their relationship with the dependent variable. Other models such as Probit model remain very identical in all other aspects to this logit model except that a different cumulative probability function is considered. In case of Probit model, normal distribution is employed. Since the model is nonlinear in nature, ordinary least square or OLS cannot be employed for estimation and therefore maximum likelihood method is often employed to estimate these models.